Morning, everybody. Today, in this lecture, we will be discussing the gas separation and purification systems. The plan of my talk is going to be like this. I will first introduce the topic. Then we'll discuss the ideal process for gas separation and the amount of work required for such a process. We will find out what is the work requirement for separating air into its various components. Next, we discuss about the Gibbs phase rule, which tells you how many number of independent thermodynamic parameters exist for either a single component mixture or multi-component mixture. The temperature composition diagrams for gas mixtures will be discussed thereafter. And we'll also see what is the cooling process for a two-component mixture, for example, nitrogen and oxygen. Its enthalpy concentration diagrams. Next, we'll discuss the separation of gases by various processes. First, we'll discuss about the separation by condensation and flashing. Then we'll discuss about the distillation, separation by distillation. Then we'll see the distillation of air by a single Linde and double column systems, argon separation system, hydrogen separation system, okay, and then helium recovery from natural gas and its separation. Next, we will talk about the gas purification systems, basically by refrigeration process or physical adsorption or chemical adsorption process. Okay, and then we will conclude this particular topic. Right. Major industrial applications of low temperature processing involves separation and purification of gases. Now, air, for example, if you distill, you will be able to get various components. The components which you normally get are oxygen, nitrogen, argon, krypton, xenon, etc. Carbon dioxide and water vapor also are present, and water vapor will condense, then becomes liquid water droplets. They need to be separated right at the beginning. Helium, which is commercially obtained from natural gas, it is also separated by a low temperature process. Hydrogen from coke oven gas is separated at low temperatures. Okay, it's called the Linde-Braun recovery system you normally use. Then important aspects of gas separation and purification are presented in this lecture. Let us look at the ideal process for gas separation. Let's assume that you have two ideal gases are present. The gas is called capital A and capital B, and they are trapped, let us say, inside a cylinder, and there are two pistons. They are frictionless, and these pistons are nomenclatured as small a and small b. See the diagram on your right hand side, and you will see that the gas is dropped in between, and the two pistons are, let us say, they are at the extreme ends. And the piston, the left end piston, we'll call it a small a, and the right end piston, we'll call it a small b. And the piston A is permeable to the gas A. Small a piston is permeable to gas A. It means when as you move the piston forward, gas A molecules will freely flow through this piston, okay, but not gas B. Similarly, the piston on the right hand side is such that it is permeable to gas B, but not gas A. So, by moving the piston close to each other, gas A will get separated to the left end of the cylinder and gas B will get separated to the right end of the cylinder. But the process of moving the pistons close to each other compresses the other gas. For example, gas A is being compressed by piston B and gas B is compressed by piston A. Originally, they are at their, both the gases are at their partial pressures, right? But after the compression, they will come back to the original pressure of the gas in the cylinder. So, but they get separated now, but they will be having the total pressure, whatever that is initially observed. So the total pressure inside will be, let us say, capital P is equal to the pressure A, the partial pressure of gas A, plus the partial pressure of gas B. Okay. Now, what is the work done in the process? So what we are doing is we are moving the piston A. Let's try to take one gas and try to see what's the sort of work done by the. We are, let us say, we will try to move the piston B, then gradually towards from right to left, and then it compresses gas A. Now this process of compression is the isothermal compression process. Okay, so you can see here in the picture, the gas is compressed isothermally. So a mass of gas is entered at an initial pressure. Okay, that initial pressure will be the partial pressure of the gas, and then it enters inside this. Now the compressor piston is moved forward so that the gas is getting compressed here. And during the process of compression, certain amount of heat will be rejected, that is QR dot. And at the end of the process, the gas is now compressed to the total pressure of the system. From the partial pressure to the total pressure, gas is compressed. Right, very good. Now let us find out what is the work done in the process. Now this can be represented in terms of a TS diagram where you have the gas at initial position 1. There is an isothermal compression process, the temperature remaining constant. So it moves horizontally in the TS diagram and reaches the point 2. Now we can calculate this based on our standard, first law of thermodynamics, which tells you Q dot net minus W dot net is equal to summation of all the enthalpies of the outlet flow gases minus summation of the enthalpies of the inlet gas. So using the above formula for the compressor alone, we can write QR dot minus W dot. QR dot is the heat dissipated, W dot is the work done. You work into the system is equal to the enthalpy of the outlets will be M dot, that is the mass flow rate, multiplied by H2 minus H1. Okay, H2 is the final enthalpy and H1 is the initial enthalpy, so it is H2 minus H2. But obviously we know H1 is larger than H2 and therefore we can write it as minus M dot H1 minus H2. What about the heat rejection? The heat rejection QR dot can be written as, it is, you are taking the entropy of the system from initial state 1 to the final state 2, and therefore the heat rejection will be M dot T1, it's at a constant temperature, and S2 minus S1. S2 is the final state minus the initial state. So this again can be written as minus T2 minus minus M dot T1 into S1 minus S2. So combine these two equations, you get the result minus W dot net is equal to M dot T1 into S1 minus S2 minus M dot H1 minus H2. Now the term H1 minus H2 will be smaller compared to the term which is T1 into S1 minus S2. Therefore, this right-hand side term is completely positive, which means the process of compression from the initial state 1 to the final state 2 is a work absorbing process. So this is the net work done. So the net work done is equal to minus W dot by M dot is equal to T1 into S1 minus S2 minus H1 minus H2. Now what does this 1 and 2 refer? 1 represents the initial state and 2 represents the final state. of the gas after combustion. Right. Now, this is as far as one gas is concerned. Now, we are having two gases in our cylinder, and we are now trying to separate these two gases. So, we should find out what is the work requirement for compressing unit mass of gas. Okay, now let's find out that. So, if you want to do that, it is now we can rewrite this as minus W dot M divided by MM. So, here W dot is the work requirement, total work requirement. M, the small m represents the mixture. Okay. The subscript m represents the mixture. Similarly, per unit mass of the mixture, W dot M divided by M dot, which is the unit mass of the mixture. Now, this is equal to, since there are two gases only are involved here, it's equal to minus W dot A MA into MA by MM. Okay, this is for the first gas, plus W dot P divided by MP into MP by MM. Or in other words, what we are writing is minus W dot A by MM plus W dot P by MM with a negative sign. And since we were just introducing MA in between, MA and MP. So now we can write W dot M divided by M is equal to Tm. So we can write for the first one. So this equation is for the first one. First gas A. So Tm multiplied by MA by MM into S1A minus S2A. Okay. Now, from the second term, we are writing MB by MM into S1B minus S2. Okay. This is the term as far as the first and second term are concerned relating to S1. There is also another term relating to H1. So that is minus MA by MM into H1A minus H2A plus MB by MM into H1B minus H2B. These are the two terms which come into. Now what we can do is, we can treat this gas as ideal gas. If you treat this as ideal gas, then S will be equal to Cp logarithm of natural logarithm of temperature minus R times natural logarithm of pressure plus some constant value. Now this, you please remember, we have given this expression when we discussed the entropy in one of the earlier lectures. Okay, and similarly, H can be written as Cpt plus HR. We can write it this way. Now, if you use this expression, let us see how exactly we can solve this. Okay. First thing what we notice is the temperature remains the same in the process. Now, so if you look at the logarithm term, anything relating to temperature remaining the same would mean the initial temperature will be same as the final temperature, and therefore logarithm of T1, so you have to apply the limits from the T1 and T2. If you subtract, the logarithm of 1 will be equal to 0. So therefore all temperature related terms and also constant terms will become 0. It doesn't exist. Okay, so we have to only consider the pressure term, because that is the one which will change from initial state to final state. So therefore, S equal to minus R, L and P. That's what we have to consider now. So let's apply this here in this equation. Minus W dot by M dot M is equal to Tm into, now let's write for the first term. The first term will be MA by MM. I am retaining this term as it is. Minus W dot A by MA, I write as minus RA ln P1A plus RA ln P2A. There are two terms now, so we are just writing the first term minus the second term. We are writing this. Then we are writing the second part as MB by MM into RB minus RB ln P1B plus RB ln P2. So we are writing. Now, the term P2A and P2B, it is nothing but PM, which is the total pressure. It is nothing but that is, the gas is getting compressed, it becomes the total pressure, right? Originally, it starts with partial pressure of the gas, After compression, it becomes the total pressure. So we have to replace this P1, P2A and P2B as PM. If you replace this and then simplify this expression, then you get the expression as TM MA by MM into RA ln PM by P1A. Similarly, plus MB by MM RB ln PM by P1. So this is what you get as an expression for the work requirement for separation of the mixture gas A and B. Okay. Now P1A and P1P2, P1B are the initial partial pressures of the gas A and B. Okay. After compression, they become the total pressure. P1A becomes PM and similarly P1B also becomes PM. Right? This is what we see. Okay. Now what we will do is we will try to use MARA is equal to NARU. What is MA? MA is the mass of the gas of A and RA is the gas constant per unit mass and Na is equal to the number of moles of gas A multiplied by the universal gas constant. So MARA is equal to NARU. Similarly, MBRB should be equal to NBRU. Okay. MBRB equal to NBRU because the mass of gas of B multiplied with gas constant per unit mass equal to the number of moles of B multiplied by the universal gas constant. So let us try to introduce this. So what we have done is here we have written exactly the same expression what we had in the earlier page, whatever we had here written here, right? Next, first let us divide throughout by the common factors, which is mm. We remove that mm, okay, which is in the denominator left hand side we divide by mm. So also that mm is removed, and so also the term on the right hand side mm is also removed. MARA we write it as NARU, and similarly MBRB we write it as NBRU. What we will do is now we will divide by the mole fraction of the total mass, the number of moles for the total mass, the complete mass. So NM you will write. Okay, you divide throughout by NM, which is the total number of moles of the gas. NM, that what is the total number of moles? Total number of moles, NM is nothing but number of moles of A plus number of moles of B. That's your total number, NM. NM, you divide by NM throughout. Yeah, that's what you have written here. Now, what we see is here, minus W dot by NM is equal to, and RU and can come out of this expression. So RU comes out, RU into TM, common factor, then multiplied by Na by Na plus NB, ln 1 by Ya. What is Ya? Ya is nothing but P1 by P1A. That is, Ya is the fraction of gas molecules in the total number of molecules. Okay, so the number of molecules will be directly proportional to its partial pressure. So PM by P1A is nothing but the inverse of 1 by Ya. Okay, just we are writing it as 1 by Ya, and similarly NB plus Na plus NB into ln 1 by Ya. What is Na by Na plus Nb? Na by Na plus Nb is nothing but Ya again. Because the number of molecules of A divided by the total number of molecules, again representing the mole fraction of A. So minus W dot by Nm dot Nm is equal to Ru Tm into Ya ln 1 by Ya plus Yb ln 1 by Yb. A bracket is missing here. You can put the bracket. So what we notice is this is the work requirement for separating just two gases, okay, from the mixture. The mixture consists of two gases, and this is the ideal work requirement for separation of the two gases. So for a K components in a mixture, instead of just two components, if suppose you have K components, we have to extend this formula for K components. So minus W dot by Nm is equal to Ru Tm. Ru is the universal gas constant. Tm is the average mean temperature of the gas multiplied by summation of I equal to 1 to K, Yi ln 1 by Yi. Yi represents the mole fraction of the gas I. Okay. And similarly, 1 by Yi will be the inverse of the mole fraction of that. So this is the work requirement, what you will have for separating K components of a given mixture. Right. Now assume that you have starting air, you are using air at 300 K and trying to separate it into various components. So what is the work requirement for separation of air into its different components? So we'll see here, you have a table which is in front of you, which tells you the gas, the mole percentage, the work required per unit mass of gas separated. The units are given in terms of kilojoule per kilogram, right? Okay. So for nitrogen, it has a molar percentage of 78.08 and the work requirement is 60 kilojoules per kilogram. For oxygen, which is 20.946 mole percentage, work requirement is 191. Okay. And for argon, which is 0.934 mole percent, the work requirement is 353.9. And for carbon dioxide, which is 0.033%, then the mole requirement is 511.1. And neon is very small, which is 1.8 in 10 to the power minus 3. And it has the work requirement is 1472.5. For deuterium, which is 1.56 e to the power minus 2, 10 to the power minus 2. This is 6090 kilojoule per kilogram. For helium, which is about taken as 10 parts in a million, the work requirement is 14,220 kilojoules per kilogram. What we notice from this table is, as the number of the component becomes smaller and smaller, the work requirement becomes more and more to separate the gas to its pure state. Next, let us discuss the characteristics of gas mixtures. Okay. Now let us discuss what is called the Gibbs space rule. The number of independent parameters or properties which are required to determine the state of a system is given by the Gibbs space rule. What does Gibbs space rule tell you is if F is equal to C plus 2 minus 1. F represents number of independent state parameters, C represents the number of components, and phi represents the number of phases. For example, just to take a simple example, let us say we have a binary system with the liquid and gas phases. So C is equal to 2, phi is equal to 2. Okay. For example, an example could be, for example, nitrogen and oxygen, which are both in the liquid and gas phase. So the number of components in this case is there are two components, nitrogen and oxygen. Number of phases that are present is, let's say, gas phase and liquid phase, and therefore phi is equal to 2. So the total number, what is required will be F will be equal to C. You put that value C, which is 2, and plus 2, C plus 2, that is 2 plus 2, minus number of phases, which is 2 again. So therefore, it will be simply equal to 1. Sorry, it's equal to 2. That means there are two independent properties are needed to specify the state of the system, right? So this is what you will have. Now suppose I would like to mention, for example, let us consider a single component system, okay? And with its liquid and phase, suppose there's liquid and phase, liquid and vapor phase or something, that is phases are 2, okay? And there is only one component. So if you substitute here, C will be 1 plus 2 minus 2. So F is equal to 1. Suppose a solid is becoming a liquid, there are two phases. So at that point is characterized by only one property. Maybe if you just define the temperature or if you define the pressure, then automatically all the other parameters are clearly defined. Okay. So This particular formula of Gibbs-Base rule is a very useful thing to tell you how many number of independent parameters, state properties are required to define the state of the system. Now let us consider the two-phase component, namely the nitrogen and oxygen, for example. Now let's assume Z as the composition of this mixture. Now Z will depend upon two parameters, namely temperature and pressure. Okay, Z represents the composition and Z will now depend upon two parameters. So if I try to plot the temperature, okay, as a function of the mole fraction, okay, of these mixtures, then you can see there are three possibilities of temperature composition diagrams. Okay, first case, where case A will consider as the critical pressure of both the components are well above the pressure at which the curve is plotted. That means the liquid state, liquid and vapor states, liquid saturation state is already there in the pressures what we are considering. So therefore, if you consider the mole fraction, okay, on the x-axis, the temperature on the y-axis, you find that there are two curves. What are the two curves? The two curves, for example, the upper part of the curve is the vapor, this part of the curve is the vapor, and the lower part of this curve is the liquid. Suppose you start with the vapor, that vapor will try to condense at a temperature higher than that of the liquid at the same composition trying to boil. So the vapor condenses at a temperature, vapor of the mixture condenses at a temperature higher than that of the liquid which is boiling at the lower temperature. So in same composition, you are taking vapor condenses at a higher temperature, whereas the liquid of the same composition boils at a lower. Okay. So there is a mixture. On the other hand, if suppose you are resorting to only one composition, one component, that means, for example, you end up with the pure component on either side, then you can see that the vapor and the liquid, they all either condense and boil at the same temperature. That's what happens. Okay. Now, if you consider the, let's say, one of the components the critical pressure of one of the component is below the total pressure of the system. Okay, that means one of them is only having a behavior of this type. The other one, you have the critical pressure of the other component is below the total pressure. For example, if you consider helium nitrogen mixtures, for example, at a pressure of 20 atmosphere, then the curve, the temperature composition curve behaves like this. You see critical point of one of the components starting at this one. The curve actually terminates in this manner, behaves in this manner. Okay. Now, if you consider an azeotropic mixture, okay, this mixture is a two-component mixture again, but at some specific composition, then again the liquid vapor curve join together and the substance behaves as though it is a pure component, pure substance. For example, if you can consider a mixture of, let's say, acetone and chloroform, for example, then you have this type of behavior. Okay. So for our present discussion, we are going to consider only the case one. That is the first case where the critical pressure of both the components are well above the pressure at which the curve is plotted. Okay, let's try to do that. Okay, so if that is the case, how does, for example, the two-component mixture starts cooling down? We start with a gas mixture at a point 1. Okay, it has a certain amount of mole fraction. So there are two components here. The two components are, let's say, nitrogen and oxygen. Nitrogen boils at a temperature of 77 Kelvin, whereas oxygen boils at a temperature of 90 Kelvin. Okay, so as a pure component. Now let us consider a mixture of nitrogen and oxygen So the composition can be varied from 0 to 1. 0 will represent the pure nitrogen and 1 will represent the pure oxygen. Okay, 0 to 1 means the mole fraction of oxygen gradually increases from 0 to 1. At the same time, nitrogen mole fraction decreases from 1 to 0. Okay. So let's try to take a gas at a temperature, a gas mixture at a point 1. Okay, you start gradually cooling this gas mixture. When you do this gas mixture gradually cooling, first it touches the dew point line where the gas condenses into a liquid. Okay. The gas will have the same composition. The gas phase will have exactly the same composition. At the same time, the liquid phase will have more oxygen component. Okay, you cool it further, then the gas phase, that as the temperature goes down, the gas phase now enriches more on the low boiling component, and the liquid phase enriches in the high boiling component. Again, as you go further in temperature and reaches, let us say 4F, okay, then all the gas is probably totally condensed, but the gas phase has further enriched in the low boiling component, whereas the liquid phase has enriched in the high boiling component. Okay, if you go down further, then it is now you are reaching the point Y, wherein there is no gas phase, the entire thing is totally liquid, and the composition exactly is the same as the composition of the total gas to start. Right? Now, what does it show? It shows that as you cool down through this dew line and bubble line, the gas composition, the liquid phase enriches in the high boiling point component, and the vapor phase enriches in the low boiling component. This is what exactly happens during the process of cool down, because the dew line and bubble line are separated for a gas mixture. Right, let's proceed further. Now, the shape of this temperature composition curve for a given mixture depends again on the intermolecular forces between the molecules. For example, this plot shows you the nitrogen and oxygen composition for example, for nitrogen oxygen mixture. It is plotted at for different pressures. The pressures is 1 atmosphere, for example, you start with, then 2 atmosphere, 5 atmosphere, 10, 15, and 20. As you notice that the dew point and bubble point curves are gradually coming close to each other when you operate at higher and higher pressures. Okay. So the separation between the dew point and boiling point curve will be larger if it is at atmospheric pressure. That's what we observe, right? Okay. Now the shape of the curve is in general the same at all pressures, and this fact that the separation between the curves is larger at lower pressures is made use of in the fractional distillation of various components. Similar curves are now plotted here for in this slide. You can see for oxygen and argon mixtures, okay, the mole fraction of argon is gradually increasing, and the mole fraction of oxygen is the maximum at the left. One value mole fraction of oxygen is 1, and on the right side it is 0, whereas the mole fraction of argon is 0 at the left, and at the right hand it is 1. Okay. Again, the same behavior is observed 1 atmosphere, 1.4, and 2. The gap between the two curves, the dew point curve and the boiling point curve, decreases with increasing pressure. A similar plot is given for nitrogen argon mixtures for 0.658 atmosphere, 1 atmosphere, 2 atmosphere, 3 and 4. So this is the composition diagram, temperature versus composition diagram for the gas mixture of nitrogen and oxygen. Right? You can also replot the above diagram in terms of enthalpy, and you come across what is called enthalpy concentration diagram. The enthalpy concentration diagram is very useful in studying the behavior of binary gas mixtures. In this diagram, what you are seeing is the saturated vapor part is plotted on the is on the upper curve, and the saturated liquid is shown on the lower curve, and the mole fraction of nitrogen is increasing from 0 to 1. Okay, and what you see is these are the isothermal curves. So if for a given temperature, the liquid, as you keep on increasing for a given temperature, as you keep on changing the composition to saturated vapor, the composition completely changes. The composition in the case of liquid state, for example, contain less percentage of nitrogen, whereas when it goes to the vapor state, it contains more amount of nitrogen. Okay, and similarly in the lower end, the liquid state, oxygen is more percentage, whereas in the vapor state, nitrogen is more is having higher percentage. So the dew point boiling point curve can be represented by the upper and lower curves. As the temperature increases, the composition changes, as can be seen from isotherms. Okay, let us now move on to gas separation methods. What are the different gas separation methods? One important method is to separate the gas by condensation and flash. Partial separation of gas is possible by the simple evaporation or condensation. In a partially condensed mixture, the liquid phase is richer in the higher boiling point component, whereas the vapor phase is richer in the low boiling point component. Now, in fact, a distillation column uses this principle by repeats this at several composition. We'll see this shortly. But the method is suitable, very much suitable for gases whose boiling points are very close to each other in the case of distillation column, whereas it will be if the boiling points are well separated, then partial condensation is very effective to separate the components. Okay. So, for example, suppose I have nitrogen and helium mixture, and this can be condensed at a temperature about 80K. It makes it possible to recover almost 94% of helium, the vapor phase, and about 0.5% mole of helium is present in the liquid state. So you can just see here this diagram, the mole percentage by condensation on condensation with liquid nitrogen, okay, the gas mixture. So how much it is in vapor, how much it is in liquid. So you are trying to condense it in liquid nitrogen. Okay, so let us say at a temperature of 78, the mole percentage of helium in the liquid phase is only about 0.2%. Whereas if you go to higher and higher temperatures, the mole percentage of helium keeps increasing in the liquid, and correspondingly, what about the mole percentage in vapor? For example, at 78 Kelvin, the mole percentage of helium in vapor is almost about close to some 95%. So fairly large percentage of gas is already separated if you cool with just liquid nitrogen, because the boiling point of nitrogen and oxygen, so nitrogen and helium are well separate. Helium boils at 4.2 Kelvin, whereas nitrogen boils at 77 Kelvin, right? So this way can separate by condensation and flash. Now, if the boiling points are close to each other, then you require a different way by which the distillation process is used for separation of the gas. Separation of close boiling point components by cascading several evaporations and condensation in a device is known as the rectification process. So, if suppose a gas and liquid, I will just explain this using this diagram once again. Okay, if you take this diagram, If you try to take, okay, we'll take, for example, the liquid and nitrogen and oxygen diagram only. We'll take. Suppose you take a gas mixture and interact the liquid mixture of the same composition with it. Okay, let's say we'll take, for example, 50%. Okay, we take this and try to combine it. What you notice is the gas mixture is at a higher temperature and the liquid mixture is at the lower temperature. When you mix them together, then the gas, they try to equilibrate. The temperatures are different, they try to equilibrate. So that means they try to come to a common temperature level, which is an average between the high temperature and low temperature. Then there is a separation that is taking place. So when the separation takes place, the gas component goes to this side and the liquid component goes to this side. So in the process, what you see is that the gas is enriched in low boiling component, whereas liquid is enriched in high boiling component. This is exactly what is being done in the distillation column. Okay. Now we'll explain the more details about the distillation column, but let's first see what is a distillation column. In a distillation column, there are a number of trays, okay, the number of plates, okay, and the hole with holes so that the vapor can interact very well with the liquid. Okay, there are two types of columns. You can have what is called a packed column or a plate column. In a plate column, there are a number of plates, whereas in a packed column, there are no plates, but they contain materials which have high thermal conductivity, okay, so that good heat transfer can take place between the vapor and the liquid. The packed columns can contain variety of packings and will provide a very large surface area per unit volume in a cylinder. Okay. Now, liquid is allowed to flow from the top. Okay. And what happens is the liquid stays. Liquid actually enters the holes in the plate, and then from there it goes down further. Also, it can flow out through the wear, and then it will come down. Gradually, liquid comes down from the upper plate to the lower plate, next to the lower plate, next to the lower plate, etc. The vapor goes from the bottom, and since there are holes, through the holes, the vapor will go out, and then it will connect, it will revert, it will combine with the liquid. So there is an interaction of the vapor with the liquid. So intimate contact happens between the vapor and the liquid, and then the rectification happens. Yeah. However, due to the poor liquid vapor in contact in the packed columns, plate columns are generally preferred, and the packed columns are normally used in liquid nitrogen plant columns, but plate columns are certainly used in large capacity distillation plants. Okay. Plate columns use vertical cylinders with the plates inside the column so that it permits the flow of fluid across the plates, and vapor bubbles through the plate, and then it gets in and then intimately interacts with that of the liquid. Okay. Now the description of the distillation column is shown here. A photograph of it is shown here. The topmost point, it has a condenser, okay, so that liquid gets condensed here, okay, and then the liquid gradually drops down to this plate, and in the plate you have a vertical part which is known as wear, so that when the liquid crosses the level of this wear, it goes to the lower plate. It also can drip down through the holes which are at the bottom. The holes are meant for both for the liquid dripping as well as the vapor flow upwards. Okay, the vapor bubbles through the liquid and then goes upwards. So you can see the number of plates, which are large number of plates are present. The gas which need to be rectified or separated, it is entered at the right composition within these plates, okay, at some intermediate location in the cylinder. So gradually, since due to the number of plates which are present, the liquid which is falling to the bottom side will get enriched in the high boiling component, and the vapor which is reaching the top will get enriched in the low boiling component. And at the top, when the liquid is condensed, now it will have a major percentage or the major percentage of the low boiling component, which is known as the top product. Similarly, at the bottom, the major percentage of high boiling component will be recovered, and that is called the boiler. The bottom side is known as the boiler, top side is known as the condenser system, right? So you get, after initially when you start, you have composition nearly the same, but gradually with respect to time, it gets separated and this process continues so that you have a distillation process. Okay. Now openings in the perforated sheets are typically 1.5 to 4 millimeter diameter with 20 mm gaps, so that the liquid will be able to go down as well as vapor will be able to go upwards towards this. The liquid flows from one side of the plate to the other and then reverses the direction of the plate below. The liquid height is maintained using a weir. Several modifications of the bubbling technique to the vapor through the liquid are employed in different columns, and the feed gas has to be fed in the column at the right composition to ensure proper distillation. So now, as you can see here, for example, this diagram shows you a vapor bubble inside the liquid. The vapor now gets evaporated. Okay, the liquid gets evaporated to vapor, and automatically, the liquid gets evaporated to the vapor. Okay, and that is nitrogen part of the liquid gets evaporated to the vapor and combines with the vapor, and some part of the oxygen in the vapor gets condensed and become more of a liquid, right? So this way, the nitrogen is converted more into gas form, whereas oxygen gets converted more into the liquid form, right? Because of the intermixing of it. Now, the separation of components can be understood by the temperature composition diagram, what is shown here. Let us assume the feed composition is at V4, where the vapor is fed at V4. It interacts with the liquid at the same composition, okay? And what happens is V4 now enriches to L4. This will try to interact with the vapor composition exactly at V3. Okay, when it interacts, then it will get enriched, liquid will get enriched to L3. Again, it will interact with the vapor from the plate above at V2, and it will get enriched to L2 and so on. So L4 becomes L3, L3 becomes L2, L2 becomes L1, and then L0 and so on. So the liquid composition enriches the high boiling component. On the other hand, the vapor composition enriches gradually towards the low boil. Okay. So the interaction occurring at every composition, the vapor emerging at the top will be more volatile component. It will be the more volatile component. The liquid at the bottom will be the less volatile component, in other words, less boiling. So the liquid on each plate is colder than that of the liquid below it, and that is, the condenser is colder than the boiler. So heat has to be added at the bottom of the column to provide the required vapor flow, and heat is removed at the top of the column to provide the necessary flow of the condensed liquid down the column. Now we are coming to the discussion of the air separation by Linde single column arrangement. Linde single column is one of the simplest commercial unit, and it is shown here. What you can see is the column with the perforated plates are shown here. You can see the perforated plates in this diagram, and the total schematic of the distillation is shown here. Okay. This is used for separating the nitrogen and oxygen. After removal of carbon dioxide and water vapor, air is passed through a pre-cooling heat exchanger. Okay, and this is the pre-cooling heat exchanger, what you are seeing here. Gas then passes through a coil at the bottom of the column, and then it gets cooled and becomes a liquid. It is expanded by a Joule-Thomson ball, and the liquid is allowed to reach the top of the column. It comes here. Okay. The cold vapor from the top of the column serves as one of the return streams, the heat exchanger, and it supplies cold to the impure nitrogen gas. Then liquid oxygen is collected at the bottom of this column here, and gas oxygen is obtained by evaporation of this liquid, the third passage of the heat exchanger. The major problem of the single column system is the oxygen. It carries away the also some part of nitrogen, and therefore much of oxygen is also lost in the nitrogen effluent system. Okay, this is a little bigger diagram of this. So the gas enters here, gets hydrogen, oxygen, carbon dioxide removal, then it gets cooled and goes to this thing at the bottom of the column where it gets cooled. Then Joule-Thomson expansion produces the liquid. Then this is the column through which the separation distillation takes place. Okay, and the impure nitrogen is taken out like this through the top from the top of the column, and the purified oxygen is taken out through this V, and then it comes out gaseous oxygen comes out through this. In the Linde double column system, two columns are located one below the other. The upper column is operated at 1 bar lower pressure, and the lower column is operated at a pressure of 5 bar. This pressure difference causes the temperature difference and also enables the operation of the column, operation of the condenser reboiler located in between the column. This is the condenser reboiler which is located in. Nitrogen vapor in the lower column condenses at 95 Kelvin, whereas oxygen, liquid oxygen in the upper column vaporizes at about 90 Kelvin. Using this arrangement, we get both the products as highly pure, both as nitrogen, liquid nitrogen, and liquid oxygen we are able to get. Now, there are inefficiencies of this column as well due to non-ideality of the refrigeration, imperfection in heat exchangers, and there are also some losses in the refrigeration, and because of which the column efficiency can be a little low. Right. Now, a detailed diagram is shown here for the double column arrangement. So the air input enters here, it enters the bottom of the column, then by a Joule-Thomson ball enters at the middle of this, then produces liquid and so on. And then outgoing vapor gets cooled, oxygen out is from here is the oxygen. And then the bottom of the column enriched liquid air is expanded, and then because of the pressure difference, it goes to the upper part. Upper part of the column is operated 1 bar, whereas the lower part is operated 5 bar pressure. So therefore, it will be able to move to the top part, becomes the liquid, and then comes down. And then liquid nitrogen, liquid oxygen, liquid nitrogen products are taken out from the middle of the column. Okay, gaseous oxygen are taken out from here, warmed up, and then pure oxygen, pure nitrogen is collected. Let's come to the organ separation system. The organ separation consists of two parts. It's a recovery subsystem first part, and then the purification system. In a conventional separation column, organ concentration is the highest at the lower part of the upper column in a double column system, where the oxygen concentration is also high. At this point, part of the oxygen argon mixture is removed and sent to an argon column where crude argon is recovered. The reboiler of the liquid argon column contains almost pure oxygen, and this is sent back to the main column. Argon is purified for industrial use by catalytic combustion of the combustion system, which is shown in figure, or also sometimes by adsorption. Okay, the catalytic combustion system is shown here. Crude argon from the main system enters here in the heat exchanger, and then it is compressed by catalytic combustion chamber. It enters the catalytic combustion chamber to remove the oxygen by combination with the hydrogen, and then it is separated by cooling water, cold water. It removes condenser to remove the water vapor here, and then it converts to water gets condensed to ice. Okay, and then it is dried out through the argon is now dried out through the alumina dryers to remove small traces of water vapor. And then it enters here, then it comes back and enters the heat exchanger and goes to the bottom of the column through the heat exchanger, and pure argon is separated at the bottom of the column. This liquid gets reflexed here to Thomson ball, so it becomes cooling further, and you get at the topmost column you get the nitrogen as output as a vapor. Pure nitrogen will be coming out, and you will also get the nitrogen vent at the topmost part of the column. So pure argon is now collected at the bottommost column, bottom part of the column. Okay. Now let us look at the hydrogen separation system. As I mentioned at the beginning, Linde-Braun hydrogen recovery system is used. It is one of the well-established methods. So you start with the coke oven gas, which happens to be the source for hydrogen. This is a mixture of hydrogen, ethane, nitrogen, oxygen, and carbon dioxide. Ethane, ethylene, and other hydrocarbons are also present, but the total concentration is approximately about 1%. A simple condensation evaporation process is used for hydrogen separation, since the boiling point of hydrogen is much lower than that of other components. In a Linde-Braun system, impurities such as water vapor, naphthalene, benzene, etc. are removed at room temperature. Coke oven gas is compressed and cooled by an ammonia pre-cooler, where some of the propylenes are all condensed. Okay, this is the diagram, which is Linde-Braun recovery system. It is for the separation of hydrogen from the coke oven gas. There are several streams, as you can see here. Incoming coke oven gas enters a compressor and then gets separated, ammonia pre-cooler. Then there are number of stages wherein you will remove propylene, ethylene, etc. Okay, and then there are columns wherein you get separate the liquid carbon monoxide and nitrogen, and you will also be able to separate the various components. You will be able to get the hydrogen nitrogen end product as a part of the total condensation evaporative systems. A second heat exchanger lowers the temperature of the gas further, where most of the ethylene and ethane are condensed. A liquid, I mean, this is probably the description. I am giving you the description of the process. What we have seen in the earlier diagram. The liquid nitrogen refrigerated condenser condenser evaporator condenses essentially all the remaining of the methane. The hydrogen, nitrogen, carbon dioxide gas mixture is the input to a rectification column, where with the liquid nitrogen as the reflex. By the process, 75% of hydrogen and 25% of nitrogen gas is achieved at the top of the column of the ammonia synthesis. For ammonia synthesis, pure hydrogen is obtained again by a condenser evaporator purifier arrangement, along with additional silica gel purifiers. Linde-Braun system is originally developed for ammonia synthesis and has been further modified as found to have many more applications. Okay, let's talk about the helium recovery from natural gas. Helium is available only 6 parts in a million in the atmosphere, whereas and hence the helium is obtained from the natural gas sources from mines, and schematic of the helium separation plant of US Bureau of Mines is shown in this diagram. The natural gas entering the system is compressed to about 4.2 megapascal and is treated to remove carbon dioxide and hydrogen sulfide as well as water vapor. The purified gas is cooled in a heat exchanger where much of it is condensed. Okay, this is the schematic diagram of the US Bureau of Mines helium separation system. Okay. Subsequent expansion through Joule-Thomson valve reduces the pressure to 1.8 megapascal or 18 bar at 128 Kelvin. Fluid enters the nitrogen refrigerated crude helium separator where 98% of the gas is liquefied. The vapor now contains 60% of helium and 40% of nitrogen. This crude helium gas is compressed, purified by compressing to 187 bar and cooling it with outgoing helium gas and sending to another nitrogen refrigerator separator. The process removes most of the nitrogen from this mixture as a liquid, and the vapor phase contains about 98.5% of helium and only 1.8% of nitrogen. This helium is now purified by charcoal adsorption and to obtain 99.95% of helium. And if you want to purify further, you use similar processes again and again, wherein it is absorbed and you get higher grades of helium. Helium commercial grades are several commercial grades are available. Purity of gas is always expressed as 495 or 595, which means it is 99.995 or it is 99.999. Okay. That's the 595 means 5 nines, 99.999 and then followed by a 5. So that is this representing the purity of gas. Okay, let us come to the gas purification system. Purification is a process in which unwanted components are removed from the gas mixture. Purification can be achieved by several methods. Three methods are discussed here. One is refrigeration, another is physical adsorption, third is chemical absorption or chemical reaction. Okay, let's go through the process one by one. What is refrigeration? Refrigeration is a simple method to remove water, carbon dioxide, and other contaminants in the process stream just by condensation or freezing. Okay. Refrigeration can be achieved either by a cold producing machinery or a cryogenic fluid, whichever way you want to do it, you can do that. The effectiveness of the purification depends on the vapor pressure of the impurities relative to the major components of the process stream. So, lower the vapor pressure, the more it is separated out. Okay. Assuming ideal gas behavior, the maximum impurity content in a gas after refrigeration would be inversely proportional to its vapor pressure. So the lower the vapor pressure, more it will be separated, right? Okay. So now, for example, if you, as an example, would you like to talk about the refrigeration? Say, we have already seen this done in the case of separating helium from nitrogen. As you have seen, the boiling points of these are very much separate, because of which the vapor pressure of helium in the nitrogen will be large, and therefore it is separated vapor, whereas the vapor pressure of the nitrogen in this liquid state will be smaller, so it will get separated very well. So nitrogen and helium get separated very well because of the process. A gas mixture gets separated very well because their boiling points are well separated. Now let's come to physical adsorption. In the physical adsorption, the gas is retained at the surface of the solid surface. So it forms retention of one. This involves the attraction and retention of one or more layers of molecules on solid surface. Materials such as silica gel, charcoal, zeolite, molecular sieves are widely used as adsorption due to their porous structures, creating large effective area. Synthesized zeolites have been manufactured with very controlled pore sizes ranging from 4 to 13 angstrom. This permits adsorption of gases on the basis of the molecular size. In the chemical purification process, the component to be removed is made to react with another component so that a new compound is formed. See, amine and similar other processes are based on the chemical purification. Typically, if you look at zirconium vanadium iron getters, they are used to absorb hydrogen in a vacuum system. Essentially, it follows the chemical reaction wherein the hydrogen goes into solid solution. See, once it goes to solid solution, fresh reactive surfaces are formed by reactivating these getters. Oxygen, for example, is also removed in a chemical process by catalytic reaction of hydrogen along with hydrogen to form water. Okay. Now, in conclusion, we would like to mention the separation and purification methods are described in this chapter. They use cryogenic techniques, while for obtaining cryogenic temperatures, these gases are required. This subject of study is quite vast, and the interested readers, students, should refer to the references given elsewhere. Particularly, I would like to mention the book on Rundall-Baron, the Cryogenic Systems by Rundall-Baron, as is an important textbook where you can get a lot more information about the gas separation and purification. Right? Okay. I thank you very much for your patient listening. I wish you all the very best and have a great day.